Okay, in this video we're going to talk about some basics of carbohydrate chemistry. So we're just going to cover a couple of definitions here, and then we're going to work through an example of how we can convert a straight chain monosaccharide into a pyranose ring. So the first thing we really want to do is just talk about some synonyms we can use for the term carbohydrate. So carbohydrate is a class of molecules. We're going to see some examples through here, and there's some synonyms we can use. So some of the synonyms that are used is they're also called sugars, and these are generally simple carbohydrates. And another term that we will see is this term monosaccharide, or specifically just the word saccharide. And that's just another term, again, to talk about these type of compounds here. So generally speaking, when we're talking about the word carbohydrates, you might say the word sugars or saccharide to talk about the same structure we're looking at here. Obviously, when we use the term monosaccharide, we're talking about one specific unit, and really in this video we're just going to be talking about monosaccharides. Okay, so let's look at a couple more examples here. So the first thing I really want to do is look at our structure here, D-mannose. The first thing we're going to examine is this letter D here and what that represents. And that D really signifies the orientation of our hydroxyl group at the last chiral center, lowest in the molecule. So again, here we're looking at a Fischer projection, and this is the way carbohydrates are normally viewed. And in the Fischer projection, when we talk about D, we're looking at the orientation of the OH group at the last chiral center, right above the CH2OH. So when the OH is on the right side, as it's shown here, that means that we have a D monosaccharide. If the OH happened to be on the left side, then this would be an L monosaccharide, or an L sugar. So most sugars are D sugars. So typically that's the type of examples that you'll see working with D sugars. Those are really the natural carbohydrates. So again, D means the OH, the last stereocenter, is on the right. So let's take now a look at this term aldehexose and kind of talk about what this term means. So aldehexose, there's really two things in here. First is the term aldo, and that really represents the fact that we have an aldehyde here. Okay, so an aldehexose represents the fact that we have an aldehyde, and you can also see the term aldose, A-L-D-O-S-E. The phrase OSE really represents that we have a carbohydrate. So here we have an aldol, and that means we have an aldose. Really, the other type of structure that you can kind of encounter is a ketose. So you can have a ketose, and a ketose represents when your carbohydrate has a ketone, and that's exactly what we see at this bottom structure here. And normally your ketone is going to be at what we call carbon 2. So we normally number from the top. There's carbon 1. So in terms of your aldose, carbon 1 is an aldehyde. For a ketose, your carbon 2 is obviously your ketone. The next thing we're going to really look at is this term hexose, and that's pretty simple. The hex just represents the number of carbon atoms that you have. So if we look in this example, we have 1, 2, 3, 4, 5, 6. So this structure here, which is called D-mannose, is an aldehexose. It's an aldehyde, and it has 6 carbons. If we look at the example down at the bottom, we have 1, 2, 3, 4, 5, 6. Again, we have 6 carbons. So we could actually call this, instead of a ketose, we call it a keto hexose. And again, OSE is what we use to determine that we have a carbohydrate here. And typically, again, you're going to see a hexose or a pentose. So you're either going to have carbohydrates with 6 carbons or with 5 carbons, and 6 is the most common thing we'll see. The next thing I really want to just talk about is this term pyranose. So really our objective here is to convert a straight chain monosaccharide into a pyranose ring. So here is our straight chain monosaccharide, D-mannose. We're going to convert this into a pyranose ring. And again, here we call the structure beta-D-mannopyranose. So we use this term mano to just tell us what carbohydrate we have, mannopyranose. And the term pyranose here is just kind of defining the type of ring we have. And this term pyranose really derives from pyran or tetrahydropyran, and basically all that signifies is that we have a 6-membered ring where one of the atoms is an oxygen. So this is called tetrahydropyran, okay, and this term pyranose comes from that word pyran, and all that really signifies is that you have a 6-membered ring where one of the atoms is an oxygen. And again, typically with carbohydrates, there are a couple forms. You can have the pyranose form, which is the 6-membered ring with the oxygen, or you can have a furanose form, and that is derived from this term tetrahydrofuran, also called THF, and that's simply a 5-membered ring where one of the atoms is an oxygen. So if we look at our structure here, I'm just going to kind of highlight our ring in orange. And here we can see that this is a chair. Here is our oxygen atom here. So again, we have our 6-membered ring, 1, 2, 3, 4, 5, 6, where one of the atoms is an oxygen. So we are going to convert our straight chain monosaccharide into our pyranose ring. So that's a 6-membered ring. We're working with D-mannose as the aldohexose and converting that into beta-D-mannopyranose, and that represents that we have our 6-membered ring. So now let's go through the process on exactly how to do this. So again, what I've done here is I've just copied the same molecule. This is D-mannose in our aldohexose form. And now I've numbered our carbons, 1, 2, 3, 4, 5, 6. And then I've changed the color of a few of these. My aldehyde is in green. The hydroxyl groups and hydrogen atoms attached to carbons 2, 3, and 4 are in black. Carbon 5, remember we said this was a D sugar because the OH is on the right. I'd made that OH into red, and then the rest of the hydrogen and the CH2OH6 is in blue, just so we can keep track of where all these atoms go. So this process isn't too complicated. The first thing that we are really going to do here is we're just going to take our molecule and flip it on its side. So the aldehyde that was on the top is now going to go on the right side. And that means any group that was on our left here, carbon 2 and OH, 3 and OH, 4 and 5 have H's, are now on the top. So carbon 2 is OH on the top, 3 OH on the top, and then H and the H on the top. So all I've done is just kind of rotate this over to get this structure here. And the key thing to recognize is kind of two functional groups here. We have an alcohol, actually let's make that in red. We have our OH in red, and remember this is the OH that caused us to say we had a D carbohydrate, D-mannose. And then we have our aldehyde in green, so I'm just going to kind of draw this aldehyde structure out. And essentially what we're going to do is we're going to form the cyclic structure here, our pyranose form, our six-membered ring. And this is a reaction that we've learned before. We have an alcohol and an aldehyde. And this structure is actually in equilibrium with the closed form. So we really have an equilibrium here with the closed form. And essentially what happens is our OH is going to attack the carbon of the carbonyl, put the electrons on the O minus, and then we'll deprotonate this O and then protonate that OH there. And the consequence of that is we now form a six-membered ring, and you can see this six-membered ring here. I've started to number the carbons, 1, 2, 3, 4, 5. And we now have an oxygen as part of our ring. So the new bond that we've actually formed is the bond from carbon 1 to our O. So this is the new bond that's formed. This type of structure is called a Haworth projection. Okay, and a Haworth projection is basically just a six-membered ring kind of drawn in 3 dimensions. So here we see these lines are thicker, signifying that this is coming out of the board towards us, where the groups in the back are going away from us. And we're going to see in a second, basically what we're doing here is we started with an alcohol and an aldehyde, and I have to fill the rest of this in, but the functional group that we're actually forming here is a Hemiacetal. And once we fill out all the rest of the structure here, I'll point out exactly where the hemiacetal is, and it really turns out that this hemiacetal is formed at carbon 1. Again, this is the carbon that was in green. So let's go through the process again of how we can figure this out. So the first thing we did, step 1 here, was really to flip this to the side. Step 2 is really recognizing that this O is going to form a new bond to carbon 1. So the oxygen attached to carbon 5 will form our new bond to carbon 1. And when we do that, this group in blue here is going to twist. So we can really number our carbons here. Here's the O that was connected to carbon 5. 5's connected to 4, to 3, to 2, and to 1. And this bond in red is the new bond from the oxygen at 5 connected to carbon 1 in green. So clearly we have to fill in some hydroxy groups, even carbon 6 here, to really finish the structure. So we're actually going to work backwards as we go through this process. When the oxygen on carbon 5 attacks here, well, we still have to figure out where carbon 6 goes. And this is actually very simple. Anytime you have a D-carbohydrate, anytime your OH is on the right here or at the bottom, when this reacts, the CH2OH group that was here is always going to be up. So what we can do now is simply draw in our CH2OH group. And again, that is our carbon atom number 6. So let's just draw in a 6 here. So anytime you have a D sugar and you form your pyranose ring, this CH2OH that was at the bottom now goes up. And then remember, carbon 5 was connected to carbon 6, the CH2OH, and then it was also connected to that hydrogen, and that means that the hydrogen is actually down in our Haworth projection. So we're going to draw our hydrogen there. Okay, so the first thing we're doing is dealing with kind of the blue carbons in carbon 6. Next, we're going to look at carbons 4, 3, and 2 here that are in black. And these are pretty simple here. Once we flip this over, if the hydrogen is on the top face, it's on the top face. If the OH is on the top face, it's on the top face. So whatever you see on the top side here is on the top side here. So looking at carbon 4, it's attached to an H and an OH. The hydrogen is up. so the hydrogen is going to go up here. So that means that we have a hydrogen in black here from carbon 4, and therefore our OH is now down in carbon 4. Looking at carbon 3, here the OH is up. So we're now going to draw our OH up, which means the hydrogen is down at carbon 3. And again at carbon 2, the OH is up and the hydrogen is down. So we'll draw that in here. Our OH is up and our hydrogen is down. Okay, so we've taken care of carbon 6, what we have in blue. We've taken care of the red O, which is part of the ring, and the hydroxyl groups are carbon 2, 3, and 4. So the last thing we have to do is take care of this carbon at 1. So I'm just going to put a green dot here and draw a couple of green lines signifying those structures. And if you notice, the OH here, there wasn't an OH, it was the aldehyde. We've just formed an OH in the process of closing this ring. And where the alcohol go is determined by this letter beta here. So there's really two choices. You can have an alpha pyranose or a beta pyranose. And in this example, I asked you to draw the beta pyranose. And what that means is the beta tells me that the OH formed from carbon 1 is going to be on the same side as the CH2OH. Okay, so because this was a D sugar, the CH2OH is up. Because this is beta, therefore the OH formed in the reaction is also up, which means the other hydrogen from the aldehyde is now down. So anytime you have beta, the OH is up on the same side as the CH2OH. Okay? If this happened to be alpha, that would mean that our OH would be down, anti the CH2OH. So alpha means the OH would be here, opposite the CH2OH. Beta means the alcohol is on the same side as the CH2OH. And the normal situation is you have a D carbohydrate and the CH2OH is up. Therefore, our OH here is also up. And that's really all we have to do to form our Haworth projection. Again, the carbon in red forms the ring, and there's our new bond there. Because this was a D sugar, it means CH2OH is up, and therefore the other hydrogen is down. For carbons 4, 3, and 2, whatever's on the top side here is on the top side here, H, OH, and OH. And for carbon 1, the term beta or alpha describes where the alcohol is, and our OH is now up. It's beta to the CH2OH. And then the last thing I just wanted to point out is I talked about having this functional group called a hemiacetal. And remember, a hemiacetal is the functional group you get where you have a carbon atom that's connected to two oxygens, and one of the oxygens is connected to an OH. So a hemiacetal has a carbon connected to two other things not shown, and then an OR and an OH. And that's exactly what we formed here at carbon 1. So if we look at this carbon here, let's make that again in green. This carbon 1 is a hemiacetal. This carbon is attached to a carbon in H, in OR, an O carbon, and an OH. So basically, this here tells me I haven't formed a hemiacetal. And that's what we get when we form our pyranose ring. We form a hemiacetal. So in the straight chain, we have an alcohol and an aldehyde. Here we have a hemiacetal structure. So the last thing we want to discuss is just how to convert to really our chair form. And there's two types of pyranose forms we can have. So again, here's the straight chain that we started with. we just talked about the conversion to go from our straight chain form to our Haworth projection. And the Haworth projection is just also a pyranose ring, but it's just basically a 3D representation of a six-membered ring. And then there's another type of structure we can have, and this is really our chair form. And in the chair form, what we're doing is basically just converting our Haworth projection into the chair. Normally, we start with a D, which means the CH2OH is up, and normally that CH2OH goes into the equatorial position. So this is the typical chair that you'll see. I guess it'll be useful for me to kind of number our carbons again here. So here I have carbon 1, carbon 2, 3, 4, 5, and 6. And all I've done is really convert this Haworth into the chair. Again, the OH here is up, so now it is up and equatorial. Carbon 2, the OH is up, now that position is up and axial. So remember, the up position switches from equatorial to axial to equatorial to axial to equatorial. So the OH is up on carbon 1 and equatorial. On carbon 2 it is up and axial. Carbon 3, our OH is up again and equatorial. Carbon 4, our OH is down and equatorial. Our H is up and axial. And then our CH2OH group, carbon 6, is now up and equatorial as well. Okay? So there's really two ways to represent our pyranose form. Either you can have a Haworth projection or a chair form representing our pyranose structure. Okay, the problem I want you to work on for class on Wednesday is to convert D-galactose into the alpha D-galactopyranose form. I want you to draw the Haworth projection and the chair. So simply convert D-galactose, the structure given, into the Haworth projection and the chair of alpha D-galactopyranose.